Hi everyone, this is Mrs. Sharrow, and in this lesson we are looking at graphing radical functions in section 6.8. And by radical functions we really mean the square root function for today. So we're going to start with the basic parent function y equals square root x, and we're going to start by making a table of values. This will give us some ordered pairs to help us see what our graph will look like. So I'm going to start with the x value of 0. We wouldn't want to have a negative x value in this case. That would result in an imaginary y value. So if we start at 0, the square root of 0 is equal to 0. If x is 1, the square root of 1 is 1. Now rather than continuing on with 2 and 3, square root 2, square root 3 are irrational numbers, and so instead I'm going to continue to choose a nice square number like 4. If x is 4, the square root of 4 is 2. And the next nice square number we could select for x is 9. The square root of 9 is 3. Let's go ahead and graph these ordered pairs. On our graph here, we've got the point 0, 0, 1, 1, 4, 2, and 9, 3. Now if we were to continue, future ordered pairs in the graph would be like 16, 4, 25, 5, and so on. But we're just going to stick with these 4 basic points to represent the graph of our parent function. Now if we connect them, we can continue this arrow on to represent or to show those future ordered pairs. Next, we're going to list the domain and range for this graph, and I always find it easy to make the graph first and then just look at the graph to help to answer these two questions. Domain is asking what are all of the x values that correspond to points on the graph. So we can see here that all of the positive x values, including 0, correspond to points on the graph. We don't have any negative x values, and so we're going to use the interval notation for this to say that our x values are all those from 0 up to infinity. Notice how we're using the closed bracket here. That means that it could include 0. If it couldn't, for a different kind of situation, we might do a curved parenthesis around the outside to say that 0 is not included, but in this case it is. Now for the range, we're asking a similar question, but this time we're doing it for the y values. So we're asking, what are all of the y values that correspond to points on the graph? Well, notice how we only have positive y values, also including 0. We don't have any negative y values. So the range in interval notation will also be bracket 0, comma, infinity. Now, we always put a curved parenthesis around the infinity because it can't actually equal that amount. It's just representing a very, very large number. So that's our parent function. We're going to continue by doing a review of function transformations to see different ways that that parent function can be changed or moved around our graph. And so for each of these examples, we're going to assume that c represents a positive number. So if we were to just simply add a number onto the end of our square root, this is going to shift our graph up c spaces. If we were to subtract a number on the outside, just as we would expect, we've seen this in the past, it's going to move it down that many spaces. If we now were to add a number on the inside of our function, inside of our square root, this is going to move our graph left, c number of spaces. And in the next one, if we subtract a number on the inside, just as we've seen in previous functions, it's going to move it to the right, c number of spaces. So that section there is what we call translations, which sounds similar to transformations, but a translation is when it's just simply moving left, right, up, or down. Next, in the next section here with the negatives, we have our reflections. So remember that when we have the negative out in front, that is a reflection over the x-axis. And on the next one, if the negative is on the inside, this is going to be the graph of a reflection over the y-axis. Now the last one here is showing a number multiplied in front on the outside of our square root. This is going to cause our graph to be vertically stretched if that number in front, c, is something greater than 1. So if it's multiplying by a 2 in front or a 3 in front, we would say vertically stretched by a factor of 2 or vertically stretched by a factor of 3. If that number in front is a fraction value still greater than 0 but less than 1, this is what we'll call a vertical shrink, or I like to say vertically compressed, and that would be if that number is greater than 0 but something less than 1. So that would be like a 1/2 out in front or a 1/3 in front. Okay, so let's go ahead and turn over to the next side. We're going to graph the following functions now using transformations. It's always a good idea to take a look at this part first and just describe the transformations in words. So based on that chart we just filled out, subtracting 3 on the inside here is going to move it to the right 3 spaces. And then adding 2 on the outside is going to move this up 2. So we're always going to start by graphing the original, y equals square root x, and we can actually just do that one with a dotted line. Then we can shift our points. So the original, we've got 0, 0, 1, 1, 4, 2, and 8, 3. And actually, we don't even need to connect that with a dotted line. Let's just get the actual points there. Then we'll do the next step of moving each point to the right 3 spaces and up 2. If you have a different color, like I'm using, that could be handy as well to see the difference between the original and our final answer. You can also just only connect the points in the final answer. You can also go back and erase those original points. You certainly don't have to, but you can. All right, let's take a look at the next one. So now we're adding 2 on the inside, subtracting 1 on the outside. So this is going to go to the left 2 spaces and down 1. So now graphing our original will be the same as what we did before, 0, 0, 1, 1, 4, 2, 9, 3. And this time we'll move each one of the points to the left 2 spaces and down 1. This is where we have a little bit of overlap in the points, where I think it could be handy to either use a different color or go back and erase the other ones. Okay, I forgot about the domain and range. So let's go back and talk about that for the first graph. We'll see how that ends up being different for the second one. So again, domain is asking what are the x values that correspond to points on the graph. So what I want you to notice here is that the only x values are from 3 up to infinity, because we don't have any x values to the left of 3. And so instead of our cutoff being 0, as it was in the original, now it's at 3. Now for the range, the y values. Notice how the y values are only values greater than 2, because we don't have anything below 2. And so the range for our y values, it's y values from 2 up to infinity. Let's do the same thing now on this second graph. Now the domain, x values, it looks like we have all of the x values from -2 up to infinity. And then the range for the y values, it looks like we have all the y values from -1 up until infinity. So that reflects that we moved it down 1. And if we do think about those transformations, so in the first one it was right 3 up 2. So see how our domain added 3 to the x, added 2 to the y. So it went to the right 3 and it went up 2. In the next one, our transformation was left 2. So the domain subtracted 2, and down 1. So our range subtracted 1. Okay, the next two problems have some translations, moving left, right, up, down, but we also have a reflection happening in this one, and we also have a vertical stretch, and this one is vertically compressed. So we have a little bit more going on here. So for this third graph, we're still going to start by graphing the original function, y equals square root x. So we've got 0, 0, 1, 1, 4, 2, and 9, 3. Okay, so again, connect them with a dotted line or just leave it as it is. Now, anytime we have anything at all in front, even if there's a negative in front, we're going to multiply the y values of these ordered pairs by whatever's in front. So in this case, we're going to multiply the y values by negative 1/2. We're going to keep the x values the same. So we've got the first y value of this ordered pair. Let's actually write the ordered pairs off to the side. So we're going to keep the x value the same. The y value is 0. 0 times negative 1/2 is still 0. So that point is going to stay where it is. Now, the next ordered pair is 1, 1. We're going to multiply the y value by negative 1/2, keep the x value the same. So it's going to be an x value of 1, but now the new y value is negative 1/2. The next ordered pair we had was 4, 2. Keep the x value the same. The y value, which is 2, we're going to multiply that by negative 1/2, and that gives us negative 1. So when x is 4, the new y value is negative 1. Last point over here, 9, 3. We're going to keep the x value of 9 the same. 3 times negative 1/2 is negative 3/2, or negative 1/2. So that's going to look something like this. So what we see here, these points in blue, this is still an in-between step because we still have that final step of moving them up 5. But notice how this represents it being reflected over the x-axis and vertically compressed by a factor of 1/2. It's half as tall as it was originally, and it's flipped over the x-axis. Okay, so we've got step 2 done. Now, step 3, to finish this up, we're going to take those step points, the points that are in blue, we're going to move each one of them up 5 spaces. So that will start to look like this. And then we'll go ahead and connect these points here, representing our final answer. Now, the domain this time, looking at the x values, we have x values greater than or equal to 0 because we did not move left or right, so that's why the domain is the same as the original. Now for the range, this one, we're going to write this one a little different. So the highest y value we have is 5. It's not going up, it's not going above 5, it's going below 5. So really the smallest y value, if you think about this continuing to kind of go down and down, as the x values get bigger, the y values are getting smaller. And so the smallest y value, we'll call that negative infinity. We always want to do our interval notation from least to greatest as we go from left to right. So this time we're going to say negative infinity up to the maximum y value, which is 5. Okay, so final graph. We have vertically stretched by a factor of 2. This one is going to be left 1 and down 3. So we're going to start the same way, graphing the original square root x, 0, 0, 1, 1, 4, 2, and 9, 3. Now we're going to multiply the y values by whatever we have in front. In this case, it's a 2. The x value for those points is going to stay the same. So if we list our ordered pairs again, for the original, 0, 0, 1, 1, 4, 2, and 9, 3, first point, the 0, 0, that's going to stay the same. The next y value is 1. That's going to multiply by 2. X value is going to stay the same. So now we have the point 1, 2. Let's erase these. All right, the next ordered pair is 4, 2. X value stays the same. We're going to multiply the y value of 2 by 2. So that's going to go up to 4. And then finally, in the last point, our x value of 9 stays the same, but we're going to multiply the y value by 2, so that's going to turn into a 6. So we have the point 9, 6. So notice how if you look at the points here in blue, it's similar to what we had originally, but it looks like it's vertically stretched. It's just a little bit taller. Now our final step of shifting our points, we're going to move them all to the left 1 space and down 3 for our final answer. So this time I'm moving the points in blue, left 1, down 3. Okay, we'll just go ahead and connect the points here in red to show our final answer. Now because we have shifted left 1, our domain is subtracting 1, so negative 1 to infinity. Our range, because we went down 3, is going to be negative 3. to infinity. Okay, so those are our graphs thinking about transformations. We're going to finish up with one final section looking at a unique scenario that can occur if there is a number other than 1 multiplied in front of the x on the inside and a horizontal shift, meaning moving left or right. We must factor out the number in front of the x to correctly see the horizontal shift. So here is an example. We've got this x on the inside is being multiplied by 4, and we have a plus 16 here. So at first glance, ignoring this part, we might think that the graph moves to the left 16 spaces, but it's actually not going to move to the left that far. Here's what the steps would look like if we factor out the number in front of the x. So we're just going to factor out a 4 from the inside, and that's going to allow us to write this as the square root of 4 times the square root of x plus 4. And this is just like what we do with numbers all the time. So we know something like square root 8 is the same as square root 4 times square root 2. As long as the two things under the square root multiply to equal the amount on this side, we can split it up in this way. Now, the square root of 4 is just 2. We still have the negative in front because there was a negative in the original problem, but then we just have an x plus 4 on the inside, not the 16. So if we were to now describe the transformations as the question is asking us to do, we can say 3 things about this. We can say that the negative in front is causing our graph to be reflected over the x-axis. The 2 means that it's vertically stretched by a factor of 2. Factor of 2. And then we can see here that because it's just plus 4 inside of our function part, we can see that it's going to move to the left 4 spaces. So I want to show you over here on Desmos, see that I've typed in the equation in its original form, y equals negative square root of 4x plus 16, and I just want you to see here that it is, again, not moved to the left 16 spaces. It's only moved to the left 4 spaces, and we can see that starting point here is at a negative 4. We can see that it's vertically stretched by a factor of 2. It's a little bit taller, stretched out in that vertical direction, and again, that negative in front is going to reflect it over the x-axis. Okay, so let's look at a few more. So in this next one, again, we're going to start by rewriting the function and then describe the transformations. So we'll keep the 2 in front. In this one, we can factor out the 9 and then split this up into square root 9 times square root x minus 3. Now the square root of 9 is 3. That's going to be multiplied by the 2 that was already there. So altogether, this is going to be 6 times the quantity x minus 3. So what's happening here with our transformations, we can say that it's vertically stretched by a factor of 6. And because we're subtracting 3 on the inside of our function, it's going to move to the right 3 spaces. All right, let's look at this next one. So now it looks like we're going to be factoring out a 16. On the inside, we still have that plus 5 on the end. This is square root 16 times square root x plus 2. Square root 16 is 4. And we have our function ready to go to describe our transformation. So here we can say that it is vertically stretched by a factor of 4. We're going to go left 2 spaces and up 5 spaces. All right, and finally let's look at this last one. This time we're going to factor out a 25. This is square root 25 times square root x minus 1. We still have that minus 2 on the end. That's going to turn it into 5 times the square root of x minus 1 minus 2. So our goal is always just to have a single positive 1 in front of the x here on the inside. So we can say now this one is vertically stretched by a factor of 5. It's going to move to the right 1 space, and it's going to move down 2 spaces.